title is Bridge Simulation on Metric Estimation on Lie group. Faut mieux le copier en local. It's better to make a copy. It's better to make a local copy.
Okay, yeah. You do it.
Yeah.
And this works, or
Yeah.
it does. Okay. Thank you for the presentation. So this work is a joint work with Sarang Joshi from University of Utah and Stefan Sommer from University of Copenhagen on bridge simulation and metric estimation on Lie groups. So first of all, I just want to introduce what diffusion bridges are and why they're interesting and why so many researchers chose to study this. Next, I will introduce Lie group valued processes and the diffusion bridge on these Lie groups before moving on to the metric estimation on Lie groups that we obtained through bridge simulation. And lastly, I will show how we can make diffusion mean estimation on homogeneous spaces. Okay, so diffusion bridges is a non-trivial problem. So the simulation of this engages a lot of researchers. And one reason is that simulating from the true distribution depend on the transition density of the underlying diffusion process. And in most cases, this transition density is intractable, which means that we cannot simulate directly from the distribution. So what people usually do is that they propose a guided diffusion that satisfy that it will converge to the desired endpoint and that its law will be equivalent to the law of the conditioned diffusion on the whole time interval. So here I just show like this is the standard case in R2 where you have some initial starting point and you condition on hitting this other point. And if this was the tangent space and you use the exponential chart, you will just get something similar to this on the sphere. So Delyon and Hu wrote a paper on how to simulate bridges in Euclidean case. And what they did was that they described this Brownian diffusion process where you have a drift parameter beta or B and diffusion parameter sigma. And then by proposing some guided diffusion, adding this drift term here, then under the assumption that sigma is an invertible diffusion, they showed that this solution is unique and it converges almost surely to the desired endpoint. The conditional expectation can be attained through the expectation of functionals depending on the path of the process y, as well as likelihood phi, once again depending on the path of y. And phi here will be easily computable. So that's the main idea, that when you have this simple to simulate process, you get a way to estimate the conditional expectations through this guided diffusion. What people have done, and me and Stefan have a archive paper where we do this on Riemannian bridges, but the idea here is you lift through stochastic development processes in Euclidean space to the horizontal part of the frame bundle before projecting down onto the manifold. When in case of Lie groups, we have that they are generalizable, so we can skip this whole process of lifting and then just go directly to the Lie group. So our goal is to was to generalize the result by Delyon and Hu to Lie groups. And one of the advantages of going through Lie groups is that in the case of matrix Lie groups, we can easily compute left invariant vector fields since they are just matrix multiplication. And we get a closed form expression for the logarithmic Lie group map. So for the case of Brownian motion, it satisfies this following SDE, where the i's are left invariant vector fields, and the drift parameter depends on the structure coefficient. The bi's are independent Brownian motions, one-dimensional, and we use Stratonovich integration here. And for Brownian bridges, as you see, and I mentioned before, they depend on the heat, the transition density of the diffusion. So in order to circumvent this problem, what we instead do is that we propose to use the Euclidean density instead of the transition density for the Brownian motion, which then we obtain a drift term which depends on the gradient of the squared distance function. And yeah, this is a result by Havarahan that whenever this converges to 0, this will approach this term here. So for Lie groups, we can interchange this this term with the Lie group logarithm map. And in this case, I mean, that is the push forward of left invariant vector fields. So the idea is that we use these gradients guiding in the normal direction or in the radial direction along geodesics. So we obtain, for example, this is a guided bridge on SO3, where you see that the black arrows here represent the conditioning point. And so this is the action of SO3 on unit points in R3. So the main theorem we have is that the solution to the following SDE satisfy that it converges almost surely to the desired endpoint. Its law is equivalent to the law of the conditioned process on the whole interval, and we can express the conditional expectation through an expectation of the functional of this y process, together with likelihood term with an explicit expression for the likelihood. In this case, this likelihood depends on the Jacobian determinant of the exponential map, which kind of modulates the curvature away from cut locus. And whenever we cross the cut locus, we get this geometric local time term. But all in all, and if the metric is bi-invariant, we can simply just substitute this Riemannian logarithm map with the Lie group logarithm map. And otherwise, we will just get a change in the phi term here. Okay, so with this simulation scheme at hand, we can start estimating parameters on SO3. So in this case, we generated Brownian motions on SO3 with an anisotropic distribution, meaning that the metric used to generate this Brownian motion is an anisotropic one. And in this case, we assume that the underlying metric is unknown, because then we will use bridge simulation to estimate the unknown density here. So for these points, for each point, we can simulate m number of bridges to obtain this estimate for the transition density P here. And the stochastic term will be the expectation over the likelihood phi here. And as you see, I haven't written it here, but we will be estimating this density here, the A. So yeah, as I mentioned, this is the scheme: generate points, simulate bridges to each of these points, and then we end up having convergence to the true underlying metric. So in this case, the red lines here represent the unknown underlying metric, and we see that we obtain pretty nice convergence in cases where we change the initial guess of the metric. So iteratively, the metric that we use to generate these bridges will change until we have convergence. And this is the following pseudocode that we use to estimate the underlying metric. So as I mentioned, it depends on you simulate bridges to obtain estimates for these phi terms, and then you obtain an expression for the likelihood, which then by a simple gradient descent, we get parameter estimation. And we can do this as well for the mean. So for future work, which is again an extension of this GSI paper, we are looking into the part where we guide towards fibers in the Lie group. So this, for example, in the case of SO3, the fiber here is just the 2D rotations in the plane, and then guiding towards the whole fiber here will give us bridges in the homogeneous space. In this case, it would be S2. This means that we iteratively have to, for each time that we take of the process, we have to find the closest point in the fiber and then guide towards that one. So with that in hand, we actually have a method to estimate diffusion means on homogeneous spaces. So the diffusion mean is defined as the point that maximizes the likelihood of a Brownian motion. So it's a generalization of the Fauché mean, and it converges to the Fauché mean when time goes to 0. So it's a mean that depends on the time parameter. So once again, we generated points on SO3, in this case coming from isotropic data, and then we projected it onto SO2 or S2. By bridge sampling to each of these points, we then obtain an iterative convergence towards the true mean point. And as you see, the likelihood here seems to converge as well. Right. So the conclusion is that we have done this simulation scheme on simply connected Lie groups, which gives us a method for intrinsically defining and estimating parameters on Lie groups. And then we have expanded this for conditioning on fibers to obtain parameter estimates on homogeneous spaces. So, thank you.